happy to get going if that sounds good. So yeah, thanks for everyone for coming to this discussion session. So I'm going to try to lead off some starter material on quantum classical interfaces and hybrid algorithms in chemistry. And so as this is kind of discussion starter material, it's not meant to be a complete review, and there's not too many new things apart from maybe some controversial things said at the end meant to stoke discussion. And the hope is to kind of take somewhere between 20 and 30 minutes and before we break out into discussion groups and then kind of furiously discuss. If groups aren't too large, maybe we all stay in the same room, but then to rejoin and then kind of come to any conclusions based on our starter questions. And so what kind of stuff do we want to talk about with quantum classical hybrid algorithms for chemistry? I think it's actually kind of even a valid question to start to ask, you know, what's a good definition of a quantum classical algorithm? And some ones you might go with are some algorithm that adapts its quantum operations based on non-trivial classical feedback, or something that uses extra pre or post computation to substantially reduce the quantum resources that you need. But how do we make this definition most useful, i.e. not everything? Because if you really take some of these definitions, or the first ones you might write down at face value, you might start to ask, well, is gate compiling a quantum classical hybrid algorithm? Is quantum error correction and the way it's done a quantum classical algorithm? If you look at the constructions, you might say, well, clearly yes, but is that the definition we want to have that kind of lumps these things in? And it's not a matter of right or wrong so much as what is most useful. And I think those are the kinds of things we can ask at a high level about this interface if we're so interested. But more generally, the kind of rough outline for this starter section that I want to give is to kind of zip through the things that usually come to mind when people talk about hybrid quantum classical algorithms, just kind of to review some of the general topics and hit on some maybe open questions, and then to end with some like kind of potential seed topics. So my rough outline is maybe I'm going to talk a little bit about variational algorithms and some linear algebra based algorithms as well. The road towards intractability and error mitigation and correction. And this will kind of push on, you know, do we consider quantum error correction and mitigation a hybrid algorithm? And then some just afterthoughts about how much we've started to pre-chew our Hamiltonians before delivering them to a quantum computer, and if there's still a lot of room left to play there. So I think we all kind of are familiar with variational algorithms in a nutshell, so I'll kind of just breeze through. You know, for chemistry especially, we're interested in rewriting this eigenvalue problem as a minimization over some parameterized state for the Hamiltonian. And it has a pretty basic loop, which is for any kind of controllable parameters that you have in your state, you're going to create a new state, evaluate this objective, and often feed it back to some classical optimizer. And we've already heard from Jens today about some of the improvements in the classical optimizer, and there's been a lot of work done in this area recently. And it's really nice because it has some kind of adaptivity that allows you to reduce errors a little bit, kind of does an on-the-fly calibration depending on what you choose as your parameterization. And it's nice because you can kind of make it work on any device that you have today with a better device giving you better answers. And so you can kind of apply this to tons of domains, but today our focus is chemistry. And I'm going to talk a little bit about at the end about what happens when coherent and incoherent errors come in to ruin your day and what that really means for your algorithm. And see, just to give kind of a snapshot, this is an oldie but a goodie just because I like the way it helps remind everyone that how these stack together. So you often have some piece of software here at the bottom, and each one of these software operations, so our quantum gates, maps to something that we do to hardware. And we measure some stuff out at the end, and we have this classical loop that just feeds back over and over again. So this is kind of the basic setup. There's a lot of ways you can improve on the individual things done here. Much larger experiments have been done that I'll talk about later, but that's kind of the gist of it. And so we, of course, lean heavily on classical optimization, and this is one of the first areas I'm going to hit in on for saying maybe it'll be an interesting topic to discuss, which is, of course, we're now all pretty familiar with the fact that evaluating these expectation values and gradients seems to be pretty expensive if you compare naively to the classical case, at least in terms of real-time execution, as in you need many samples, and our samples aren't quite as fast as on the classical device. And this means that inherently all of our optimizations need to be bound to kind of stochastic optimizers. At least these are the ones that seem to work best. And you heard a lot about this from Jens earlier. These are kind of the ones that are most stable. And we've made, of course, a lot of progress. And I remember presenting a version of this slide some years ago at APS, where I implored people that the right way to look at this was not to take some classical optimizer with number of iterations at the bottom and the objective progress, because you could hide in that something that might take the quantum computer 1 million years to evaluate, and instead to make it something proportional to experiment or human time. And I think there's been amazing progress on this problem, and I'm very happy about all the developments, but for the purposes of a discussion section, maybe we should ask ourselves, is this harsh scaling that's typical for quantum circuits true for all quantum circuits, or can we borrow ideas from, say, machine learning, where sometimes you sacrifice expressibility for trainability? Are there some cases where we could kind of shortcut some of these estimation problems? For example, if we made larger blocks of our circuits commuting, so we make them a little bit weaker in some notion, but perhaps ease this burden of estimation of either energy, gradients, or something else? And I don't have an answer to that question. And can we get closer to a classical scaling for gradients? And this means both in the precision and the amount of information we get back from each individual measurement. So then, of course, moving beyond just this optimization picture, there's kind of a family of methods that we've noodled a little bit on, and others have as well, that I think has some promise for a number of reasons, which is if you have some parameterized state, you can not only do these kind of nonlinear optimizations, but you can actually lean on the linear aspect a little bit as well. And what I mean by this is if you just take whatever state you have, there's now kind of a general class of methods where you do a few extra measurements on that state, set up a generalized eigenvalue problem, and you get out a lot more than you think. And I'll survey a few of those here and some of the extensions that have been done after the fact. So the general idea being of this kind of quantum subspace expansion is learn the action of the Hamiltonian in a subspace. So you already have some state. You choose some set of operators O, which is kind of where all the magic is. You act on this state with the Hamiltonian, probe on it with the other side of it. And at the end of the day, all you're doing is kind of changing the measurements you're doing to the same state and plugging it into this generalized eigenvalue problem. And sort of one of the applications of this, especially for chemistry, was that we noted with a lot more measurements, you could kind of deal a little bit with this problem that sometimes gets glossed over, which is we care not only about method accuracy, but also representation accuracy, meaning larger and larger basis sets. And I know there's been a lot of progress in doing this in other ways on quantum computers, but it kind of is a nice example of something that fits into this framework where you kind of project yourself into this kind of interaction between the active and virtual space in a convenient way that really just borrows from the traditional techniques of chemistry and configuration interactions in a very straightforward way. And it kind of allows you to get more accuracy with fewer numbers of qubits, so long as your active space was a well-chosen active space. So I won't belabor that too much. But this is kind of also the similar flavor of methods that have been coming out that try to lean now more on the linear algebra techniques that have been very successful in correlated chemistry. So for example, Langchos algorithms, Davidson, et cetera, there's of course prominent use of those classically, and now more and more import of these techniques into the quantum device because it's sort of a natural choice. Your matrix vector products are now kind of a much more amenable thing when your state is exponentially large. And so it's kind of the similar flavor. You're taking these matrix elements Hij, but your Krylov subspace is now like powers of H that you can choose, and you can plug this right back into your generalized eigenvalue problem and get answers in these Krylov subspaces. And of course, you can complain that these operations are not unitary. And there's been other work that argues, of course, that you can just express the same kind of span of these functions using this Fourier completeness of just e to the minus IHT, but you start to drift out of the disk regime when you do things like this pretty quickly. There's also been some work showing that another way to view these is if you just build functions out of the powers of the Hamiltonian, you can implement any function of that Hamiltonian you want under a little bit of restrictions. And basically your idea is just to build a projector in spectral space and get out the state you want. And of course, this has restrictions, but it's still an easy thing to kind of fit into this framework. And the challenge that you often find is as these states start to drift together, orthogonalization at high precision becomes more and more challenging. And so kind of the open question in this area is how do we kind of finish off what we like about some of these linear algebra techniques? Can we get nice high precision orthogonalizations, and can we get them approximately in the near term is also, I think, an interesting question. And the surprise for us, at least, and this applies, it turns out, to all of these methods, is they all tend to mitigate incoherent errors pretty dramatically in experiment. And this really depends on your choice of O. And so it took us some time to figure out why this was the case. Why should you be able to take a density matrix, do a bunch of measurements to it, diagonalize something, and get a dramatically improved answer? And it turns out that this is because when you set up a problem like this, so imagine now that these M's are the operators you're choosing, and you ask a question, if I want to minimize the distance to some code space and also minimize the energy of my Hamiltonian, so right back to that beautiful variational principle, this problem, while it looks complicated in the way I've written it here, has an exact solution, which is just the generalized eigenvalue problem that I wrote down. And historically, of course, we just guessed this form because we were chemists and coming from that background, but it was nice to kind of see it come back around as the exact solution to some well-defined problem that had relevance in sort of quantum error correction and the theories around there. So, and it's kind of a, I think, nice question to think about. How do we best mix in these types of operators that balance error mitigation as well as reducing the errors in our energy outright? And of course, there's been a lot of progress in quantum simulation, and the topic of error mitigation brings me to a larger one, which is, you know, we've now done larger and larger chemistry experiments. You may have seen the Hartree-Fock on a superconducting qubit experiment paper, which boasted a variational circuit that looked impressive in size. And of course, many people here know both that this was done on a chip that in principle has in the neighborhood of 50 qubits, can do many, many gates. And then of course, Hartree-Fock is a vast approximation to the thing that we're looking to do. So there's like this huge redundancy. And even still, this experiment only went up to 12 qubits. Why did it go up to 12 qubits and not 50? So I think this is kind of an important point to think about anytime you're asking about this quantum classical interface. So if I just do a little bit of a back of the envelope calculation, that in saying my goal in quantum simulation of chemistry is simulating as interesting a physical phenomenon as close to classically intractable as possible. And so what that's not is just looking at the largest possible experiment you can squint at and see a curve and hope for the best. And my prediction is that it's going to be really, really hard to actually go beyond 20 qubits without error reduction techniques, even with great fidelities. And you can sort of evidence yourself this a little bit by just setting up kind of a toy situation where you imagine that you have 3 nines, 2 qubit gates. You make some block that's kind of on 20 qubits and just kind of depth 20. You find that your overall fidelity under this very simplified model is about 80%. You say, wow, it's a decent fidelity. And then you map this back to, say, the hydrogen molecule, and you make the simplifying assumption that my circuit in my design was so good that every error took me only into the first excited state, and the gap of hydrogen is about half a Hartree. And so if you make this approximation, you find that your error in the ground state is about 0.1 Hartree, which is well off from where you'd like to be. And so this is kind of both too optimistic and too pessimistic at the same time, but it tunes you into this problem that if you're not careful, even a little bit of fidelity loss makes it really hard to compete as your number of qubits grows. You might even start to do worse than Hartree-Fock if you're not careful. And so what was the focus of this early chemistry exploration was in part that this primitive is very important for some of the later fault-tolerant algorithms that we want to do. But it was also in that to get these answers, we needed already a lot of error mitigation. So it was kind of a larger experiment still for for today, which is 12 qubits, 78 2-qubit gates, and 114 single qubit gates. And as one should be quick to point out, there's an exponential redundancy that we're using here, and that we're occupying the free fermion space as opposed to the full space. And similar to error correction, we can try to lean on that redundancy to reduce our errors that we're looking at. And so you can see that if we were left with just the raw answers over here on the right, our energy would be so far off that we would be reluctant to call that anything we would, write home about. And we have to apply multiple techniques, including post-selection and then purifications that can only be done on these Hartree-Fock states. And again, this like VQE loop that brings it down even further, but this is already kind of a Herculean task, and we're only at 12 qubits. And we kind of take the same ideas and push them on an interacting Hubbard model, where still you'll notice that we went to 16 qubits. And now we're in the hundreds or thousands of gates, but the big focus is that every time, if you just start from these raw answers, we still have to post-select, we still have to calibrate again, rescale, and then you kind of finally have some extrapolation that lines up with your predictions as well as you want. And so this is supposed to be about, the quantum classical interface, right? So let's talk about where that comes in. So if I imagine that this tiny little daemon here is a very intelligent daemon, and it plays the role of my classical computer. Maybe that's the classical computer in error correction or one in error mitigation. And he's so smart that every time the wrong answer comes through, he can stop it with absolute certainty, and only the right answers pass through. So the amount passing through, or the time it takes as you start sampling these things is like 1 over the fidelity, basically, or the number of repetitions required to see what I'm looking for. In realistic cases, we often can't get perfect post-selection. We have techniques that average things out through various techniques. So our time to getting the right answer scales often more like 1 over fidelity squared or 1 over fidelity to some power. So how does that influence us? Let me take some application block. Maybe it's made of n arbitrary rotations and n over 2 Clifford gates that I just kind of glued together. And in case it wasn't clear for context, this is the part of the talk where I'm being a little bit more controversial to hopefully stoke discussion. So if you feel a deep sense of rage about some of the things that I'm about to say, use that to fuel your discussion questions. So that'll be good. So we'll just put together this NISC application block where I put together n arbitrary rotations, n over 2 qubits. And let's do a little bit of a back of the envelope calculation. Let's say I have some circuit that exactly produces the thing that I'm looking for. It is the perfect circuit. I have an observable on that I'd like to measure. Maybe it's like a local Z operator, and I'd like to know it to precision, say 0.01. And my device can do repetitions of about 10 kilohertz. But the most time I'm willing to wait, either because my device will drift or go offline, or I don't have enough money to fund running this device for longer than this, is about 1 day. So what happens? So if I just back of the envelope number of samples required to achieve this bound, and I kind of say that, well, each one coming through is about 1 over fidelity squared, because I'm only averaging things out and I want it to be less than 24 hours. This means my overall fidelity needs to be better than like 3 times 10 to the minus 3. What does that mean for my circuit block? If I have 3 nines gates, that means I can do some fungibility. I'm assuming there's no idling errors and things like that. That means I get about 6,000 gates, period. And this is kind of an exponential wall with regards to fidelity. So you can fudge around with this a little bit, but you're going to get an answer that almost always ends up in this neighborhood with this fidelity. And that means I can work with about 50 qubits using 80 layers of gates, or 80 qubits using 50 layers of gates. This is a pretty hard wall. Once I go beyond it, I now have to wait longer than a day to get a single local observable, and I'm no longer in a regime where I think I can do very well. And if you look at these numbers, you first think, well, at least we're still in the classically intractable regime. But for applications like chemistry, are you? There's some active space methods that have now pushed what you would call 100 or 150 or maybe beyond that in qubits. And so you're going to have a really tough time if you're kind of coming by the skin of your teeth. And things are a little bit better if you can get this daemon that can perfectly identify things so it can post-select. But even then, you're kind of in the 100 qubits to 80 layers regime. So that's going to be a little bit hard to work with. And the resolution for this is, of course, in the general case, quantum error correction, where your daemon is very, very smart. But the other statement to make here is that the resolution is to either bump up the fidelity or make the fidelity matter less. And either statement basically means doing non-unitary operations. And so either specialized error correction, dissipative or contractive circuits, or something where you're now talking to a very non-unitary thing, and keeping to the theme of this talk is hence a very quantum classical interface thing that is well suited for this operation. So the final topic I was just going to mention in one slide is that I think there's been a lot of nice work in taking, this problem of putting a chemistry problem onto a quantum computer and spending more and more and more time pre-digesting that for a quantum computer. And an open question here is, have we reached the limit of what we can do there? Or can we perhaps spend even more time on the classical side to reduce the quantum costs? Maybe with these matrix product operators or some tensor decomposition of an operator. It's very well aligned with quantum circuits. So with that, hopefully I've left plenty of time to break into discussion sessions, and just to give us some seed questions, though you need not follow these if you feel inspired to discuss another topic. What was a useful definition of quantum classical hybrid algorithms? Sampling noise seems especially painful for chemistry and gradients. Have we saturated what we can do here? Should we be willing to sacrifice expressiveness for trainability? Maybe even reducing quantumness to get a little bit further? How close are we to these error mitigation limits? How do we get to the first examples of algorithms that correct rather than just detect or project without moving to the full machinery of, say, the surface code? And are there some more tensor methods on the horizon for further compressing the Hamiltonian for simulation? So with that, I've kind of just hit a range of topics about the quantum classical interface. I don't claim that it's complete or that I've touched on everything, but hopefully now we're well suited to break into discussion groups. Choose any of these topics. Hopefully you can nominate one person in your discussion group that can report back. And I think we should report back at least 15 minutes before the hour. So each group representative can say a few minutes about what they learned or talked about in their discussion section. And I can recap this all tomorrow for everyone.